In this lecture, we will discuss about the turbulent boundary layer. And in turbulent boundary layer, so I think you already know the phenomenon of the boundary layer. For example, we have a flat plate like this. So when the free stream velocity comes in, so at first the laminar boundary layer will be occur, and then and then the transition comes in, and then finally the chaotic type of boundary layer, which called the turbulent boundary layer, will occur. So in some situation, when your velocity is not too high, you maybe have a situation like this. So mean at first half of the plate, so the laminar boundary layer will occur, and then it's continue with the turbulent boundary layer. Normally in textbook, they will discuss as fully laminar boundary layer. Here means 100% is laminar boundary layer, or fully turbulent boundary layer means that at the start point here at the leading edge, we assume that there are no laminar boundary layer, so 100% will be the turbulent boundary layer. So previously in chapter 4, we introduced a few velocity profile as shown in this slide, and all this velocity profile is used as laminar boundary layer. So if you have problems and then you don't have any velocity profile, if you assume that boundary layer is laminar boundary layer, you may use equation from Blasius exact solution, because Blasius exact solution is the representative solution for laminar boundary layer. To solve turbulent boundary layer, we have two methods. Method 1 is called power law form. It is easier, however, it is less accurate compared to the second method. And then the second method is called empirical form. So it starts from the Navier-Stokes equation, and then we use the same idea of the Blasius exact solution. We calculate, we calculate every parts of the molecule, and that's why it's become more complicated. However, the answer that we get from the empirical form is more accurate compared to the first method. So in this first lecture, so I would like to share with you how to determine the drag force, the boundary layer thickness, if our boundary layer here is turbulent boundary layer. So first method is called power law form. In this method, we feed the data for the velocity profile with power law equation. So the idea is, if we have a flat plate like this, and we assume that the boundary layer is 100% turbulent boundary layer. So normally the velocity profile, okay, if we plot one by one here, it's maybe look like this, means that the arrow here is not stay in one pattern. So it's because the boundary layer, turbulent boundary layer, it is chaotic. So what we do is we make an assumption of the pattern of the velocity profile. So we assume that maybe the profile can be plotted by using the idea of power law. So means that we assume that the velocity profile can be plotted by using this basic equation. So which is u over u equal y over delta to the power of 1 over n. However, the power n here, the integer for n here, is depend on the Reynolds number value. So if we assume that the transition from the laminar to turbulent occur at 5 times 10 to the power of 5, and then the limit is until 10 to the power of 7. So means that we could use n equal to 7. So and then this is n equal for 8 for this region and n equal to 9 for this region. So and then the way we solve this problem is similar with the idea of laminar boundary layer, means we are using von Karman equation. However, in von Karman equation, we are using Newton's law of viscosity equation, which is tau is equal du dy at y equal to 0. However, for turbulent boundary layer, the idea of Newton's law of viscosity here cannot be used. Because, for example, if we have u over u, y over equal to y over delta 1 over 7. So if we do the du dy, we will get this value, we will get this term, and then when we'll substitute the value of y equal to 0, the value of du dy is equal to 0. So the mathematic solution is correct, but it would not reflect the real situation. So means that the usage of this calculation cannot be used for for turbulent boundary layer because it not reflect the real situation. So however, we still need the value of shear stress because we want to equalize what we get from the von Karman equation. We will use the idea of shear stress here, calculated empirically using the Blasius formula. However, to make sure that a student could answer this question, so normally the Blasius formula for the turbulent boundary layer will be given in the question. If you do research on boundary layer research, you need to calculate, you need to have your empirical relations, your Navier-Stokes equation, and so on and so forth to get your own value of shear stress by using the Blasius formula. Okay, let's say normally in laminar boundary layer, if you don't have any velocity profile, you will use Blasius exact solution. Okay, similar with the turbulent boundary layer, if you are not sure what a velocity profile that you could use in your research, so and then if the velocity is not too high, so means that if you are not solve jet fighter condition, for example, because jet fighter needs to move more than Mach 1, so if you just solve normal ship in the ocean or normal passenger car condition, so it is okay for you to use velocity profile of y per delta to the power of 1 over 7. That's why this velocity profile is called 1/7 power law, because many application which is not in high-end situation, so normal application can suit with the velocity profile of y over delta to the power of 1 over 7. So and then the shear stress relation means the value of shear stress calculated by Blasius solution can be written as this one. So however, shear stress relation will be slightly different when velocity profile change. This relation will be given in the question. In real case, it must be calculated using empirical method. So this is the quite common shear stress from the Blasius solution. So however, in test or final exam, we will give you this value, and then please be careful because the value at the front here will determine the final answer. Sometimes we change a little bit. For example, we change into 0.0228, for example, to make sure that you will have a unique number in your final exam. And then in this slide, I would like to show you how we could calculate the boundary layer thickness delta for turbulent boundary layer. So I could show a little bit faster here because the step is same with the laminar boundary layer. So we will use von Karman equation. So this is von Karman equation, tau equal rho u square d theta dx. And then because we have a theta here, so means that we need to calculate the theta for the velocity profile of this one. So we substitute the value of this one into this equation. So and then we will get it is equal to 7 over 72 delta. So and then we substitute into this one. So we have this one, and then we could simplify it as this one. So we have one equation of theta. One equation of tau, the shear stress, and we could say it is equation number 1 here. So and then we cannot use Newton's law of viscosity. However, we already have the value of shear stress from the Blasius calculation. So it is 0.0226 as shown in this slide. And then we equalize these two values. So the shear stress from the Blasius calculation and the shear stress that we get from the von Karman equation. So we equalize it, and then we can calculate the value of delta. So the step is similar with the laminar boundary layer. So we bring all the value of delta and d delta in the left side, and then we bring everything to the right side. We integrate both terms, and then we could get this one, and then the constant of integration will appear. So we substitute the boundary condition. So at x equal to 0, the boundary layer thickness still not occur. So then the value of c here will equal to 0. Then we will get this equation. And then I think you know how to solve this one. So from these terms, we could get the delta is equal of this one. And then it is good for you to change the term here in term of Reynolds number. So finally, we could get delta is equal 0.3721x over Reynolds number of 1 over 5. So and then we could calculate the displacement thickness and delta star. So we have the velocity profile of this one. This is the equation of delta star. So we could get, and then we substitute the value of delta as we get from the previous solution. So and then finally the delta star can be solved as 0.0465x over Reynolds number to the power of 1 over 5. So and then to calculate the theta, so previously we know that theta is equal to 7 over 72 delta, and then we substitute the value of delta, we get it is 0.03686 over Reynolds number to the power of 1 over 5. So and then we calculate the shear stress. Again here, please do not use von Karman equation, because in von Karman equation we have tau equal rho u square d theta dx, because the form here is still in differential form, so means that the equation is still not complete. So means if you could use this idea, the von Karman equation, to get the value of theta, but you need to do the integration to make sure that you the differential form is disappear. So I advise you to use the shear stress from the Blasius solution here. So we substitute with the value the delta here, and then finally we could get the tau is equal to 0.0289 rho u square over Reynolds number to the power of 1 over 5. And then we could calculate the drag force. So this is the idea of the drag force. We substitute the value of tau, and then we do the integration. And bear in mind that the Reynolds number here So Reynolds number is rho u x over mu. So means that you need to expand the Reynolds number here because we need to integrate to dx. And then if you do that, you could get the value of drag force as shown here, 0.0361 rho u square BL over Reynolds number to the power of 1 over 5. So the BL here, so B is the width. So let's say we have a flat plate like this. So B is actually the width of the plate and the L here is actually the length of the plate. And then we could calculate the drag coefficient. So if the symbol is capital D, so mean it is the average, the overall drag coefficient. So the idea is this one. So and then we substitute the value of force, drag force here. We could get it is equal to 0.0722 over Reynolds number 1 over 5. In this lecture, I will share with you the basic idea of the empirical form to solve turbulent boundary layer. The empirical method of predicting turbulent flow quantities on a flat plate with zero pressure gradient is based entirely on data. It is more accurate than the power law form, but also more complicated. The time average turbulent velocity profile can be divided into two regions, the inner regions and the outer regions. So the velocity profile for inner region is defined as this one. And the velocity profile for outer region is defined as shown in this slide. U infinity means the velocity from the free stream velocity minus u bar over u tau, and then we could plot that of the function of y over delta. So normally in textbooks, we could have this kind of graph. So what we need to understand here, it is actually the plot graph according to the empirical method. So we get the value of this one over this one, and then we plot it, and we could find that it is actually the distribution of data. So and then previous researcher will curve fitting, and then we could have the idea of these terms and these terms. So because finally we will use the idea of 2.44 ln u tau y over nu plus 4.9. So means that this equation actually it's come from the curve fitting from the empirical method. So I'm not stressed in the derivation of this equation because it is just to make sure that this chapter can be solved in a final exam. So I just it is better for us just to know the common equation for this empirical form. So to simplify this one, we could say that the equation above involves the shear velocity u tau, which depends on the wall of shear stress tau naught. There are several such relationships used. One that gives excellent result is shown in this one. So if you read in textbook, you will find that there is a lot of correlation method that are used by the previous researcher. But to simplify this one, we use the very common assumption for the CD, for the local skin coefficient. So the local skin coefficient that can be used to represent the empirical form is shown in the slide, which is 0.455 over ln 0.06 Reynolds number squared. This local skin friction or local drag coefficient allows us to determine tau naught and thus u tau at any location of interest. The velocity profile can be used to calculate quantities of interest, but u tau must be known. Assuming turbulent flow, the leading edge, the shear stress can be integrated to yield the drag. Then the skin friction coefficient can be simplified as this one. So we have CD equals 0.523 over ln 0.06 Renault square. This relation is very good and can be used up to Renault number 10 to the power of 9 with only an error of 2% or less. Even at Renault number 10 to the power of 10, the error is about 4%. And then finally, we could summarize the equation as shown in the slide. U over U tau equal 2.44 ln U tau delta over nu plus 7.4. This equation allows an easy calculation of delta by knowing the value of U tau. And then this is nu, which is the kinematic viscosity. Okay, let's say we have an example here. Estimate the boundary layer thickness at the end of 4.5 meter long flat plate if wind flow on it at 30 meter per second. Also calculate the drag force on one side if the plate is 3 meter wide. Use the empirical data. Assume that the temperature is 20 degrees Celsius. So this is the properties of air at atmospheric pressure. So it means that if you want to calculate accurately, so let's say we have a 20 degrees Celsius, so means that you need to use data for 20 degrees Celsius here. The boundary layer thickness can be calculated by using this equation. However, we need to define the value of shear stress U tau. So we have a few equations that can help us. So first, the U tau is equal tau naught over rho. And tau naught here can be calculated using tau equals CD 1 over 2 rho U square. And the value of CD can be calculated as 0.455 over ln 0.06 Renault number square. So the Renault number, we calculate from the data from the question, we could get it is 1.9 to the power of 6. So we assume that it is turbulent. So and then we calculate the Renault number. We calculate the ln here, so we get it is 13.1926. So and then we substitute, we could get the value of tau as 1.416 Pascal, and then we could calculate the value of U tau here. It is equal to 1.084 meter per second. Then we substitute into this equation, so we know the value of kinematic viscosity, and then we know everything is here. So the value of U here is the free stream velocity, so it is 30 meter per second. So and then we could determine the value of delta as 0.05567 meters. So drag force can be calculated by using this equation. First, we calculate the value of CD. So from the data, so it is equal to 0.003. So and then we use the common equation for drag force. So and then we could get it is 21.94 Newton. So this is example 2. Estimate the maximum boundary layer thickness and the drag due to friction on the side of a ship that measures 40 meter long with a submerged depth of 8 meter, assuming the side of the ship is approximated as a flat plate. The ship travel at 10 meter per second. Use the empirical methods and compare with the result using the power law model. Let's say we take properties of water at 5 degrees Celsius. We could calculate the tau naught here. We get it is around 82.80 Pascal. And then we could calculate the U tau, and then we get it is 0.288 meter per second. So from this calculation, from this equation, we could get that the delta is equal to 0.384 meter. So and then we could calculate the drag force. We start from the calculation of CD, and then we get the drag force here. It is around 30,464 newtons. So and then if we want to compare with the power law, first we need to determine what is the power that we could assume the situation. So we check the Reynolds number. So it is around 2.6 times 10 to the power of 8. So according to this table, to this range, we could assume that the velocity profile is actually u over u, y over delta to the power of 1 over 9. So and then we just assume that the shear stress from the Blas's calculation can be equal to this value, and then we could do the calculation based on the on our previous lecture. We could get the shear stress is equal to this one. So we from the von Karman equation, so we equalize these two value of shear stresses. And then we could get the delta is equal 0.358 meter. So if we compare the value with the empirical method, so 0.384 is from empirical method, and this is 0.358 from the power law method. So we found that the difference is about 6.77%. So the difference is not too big, so it's still around less than 10%. Okay, so and then if we find the value, it is around 0.02 meters, so it is around 2 centimeter difference of the boundary layer thickness. And then we try to compare the drag force. So according to the power law form, the drag force is 23,511 Newton. So if we compare with the empirical method, so we found that the error is quite big, so around 22.82%. So this maybe will interrupt or will give us a little bit false perception of drag force between the power law and the empirical methods. So I mean, if you really need if you do research on drag force, maybe this difference of drag force will influence your result. In this slide, I would like to share you how to determine the force and so on if the laminar boundary layer is still need to be counted. So means in this situation, we call as the laminar and turbulent boundary layer. So what we mean by laminar and turbulent boundary layer, we assume that the existence of laminar boundary layer at the beginning of this flat plate cannot be ignored. So it needs to be counted. So what is the effect? The effect is if we calculate by using the idea of 100% turbulent layer, actually we give or we create a false boundary layer from the beginning. So means that if we assume it is 100% turbulent boundary layer, means maybe we create a false boundary layer image like this. So means that this area is actually not covered by the boundary layer. So at the same time, if we assume that we use the calculation for 100% laminar boundary layer, so means that actually maybe we could only calculate this area. So means that the area here is not calculated. Okay, so here the idea how to calculate this situation. Okay, so means that first, because at the beginning here, the laminar boundary layer was occur, so means we could determine what is the length of this one. So and then from this point, so the turbulent boundary layer occur. And then because this point is actually not the starting point of the turbulent boundary layer because it is not on the surface. So if we project this turbulent boundary layer, we could assume that actually the turbulent boundary layer start on this point. So means that we need to calculate what is the length of turbulent boundary layer from its starting point here to the edge of this plate. Because if we see very carefully on the derivation of the boundary layer equation, we found that we use the boundary condition of x equal to 0 and delta is equal to 0. Means we determine the boundary layer start from its starting point. So means for this turbulent boundary layer, we need to determine from this point. And then another things that you need to understand is at this point, so it is actually a sharing point between the laminar boundary layer. So the idea is the height of this one, the height of this can be determined as delta. So mean this delta can be calculated by using the idea of turbulent boundary layer, because this point also occur on turbulent boundary layer, because it is actually transition between laminar and turbulent. Means that this point is a sharing point between turbulent boundary layer and laminar boundary layer. So what is the Reynolds number at this point? So we assume that this occur at the Reynolds critical, which is normally 5 times 10 to the power of 5. Okay, so from this basic idea, we could start our calculation as this one. Let's say we have a situation like this. Estimate the boundary layer thickness at the end of 4 meter long flat plate if the air free stream velocity is u 5 meter per second. Predict the drag force if the surface is 5 meter wide. With a condition of A, neglect the laminar boundary layer, and B, account the laminar boundary layer using Reynolds critical 5 times 10 to the power of 5. In this case, the velocity profile of laminar and turbulent layer is not mentioned. To simplify this calculation, we could take, for laminar boundary layer, we could take Blasius exact solution as our representative and 1/7 power law as the representative for turbulent boundary layer. This is just to simplify our calculation, because both of the equation is already discussed in our previous lecture. So we start with A. So we neglect the existence of laminar boundary layer, means we assume that it is 100% turbulent boundary layer. So we could check the Reynolds number. We get it is 1.25 times 10 to the power of 6. So means it is turbulent. So and then we could use the idea of power law. We could get the delta is around 0.0917 meters. And then we could calculate the drag force using the CD here. So we get it is 1.28 Newton. And then we try to focus on this one. First, we need to determine whether the laminar boundary layer is need to be counted or not. Okay, let's say because we assume that the Reynolds critical is 5 times 10 to the power of 5. So we calculate what is the distance of the laminar boundary layer. So if we have a calculation of this one, we could calculate the value of x here. So the x here is equal to 1.6. So if our total length is 4 meter, so means that the 1.6 is too large to be neglected. So it is around 40% from the whole plate. So means that it is not good for us to ignore the 40% effect of laminar boundary layer in our whole calculation. So and then we need to determine the thickness of boundary layer at the end of laminar boundary layer. So because there are no velocity profile, so we just use the Blasius exact solution. So we could calculate the delta here by using this equation. So we could get it is 0.0113 meter. And then, as I said, we have a laminar here, and then we have a turbulent. So, and then this point is actually the shearing point. So, and then the thickness of this boundary layer can be calculated by using the 1/7 power law, because this is also the boundary layer thickness for the turbulent boundary layer of this one. So this is the equation of the turbulent boundary layer from the 1/7 power law. And then if the delta here is equal to 0.0113 meter, we could get the value of x here is equal to 0.292 meter. So means that we have a laminar boundary layer here. So, and then it is equal to 1.4 meter. So, and then if we use the thickness of this one, we could calculate what is the starting point of the turbulent boundary layer here. So, according to the calculation, so the value of this one is equal to 0.292 meter. So now we could calculate what is the total length of the turbulent boundary layer by using this equation. So mean the length of the turbulent boundary layer can be calculated by the idea of the total length of flat plate minus the distance of transition. So means the distance of this one, the distance of laminar, and then we add the distance of this one. Okay, so I hope you understand this idea. It's quite simple if you really understand the meaning of each terms here. So, and then if we calculate that, we could get that the total length of turbulent boundary layer, it is equal to 2.69 meter. It is mean that to calculate the turbulent boundary layer by using turbulent boundary layer calculation method, we only need to consider plate length of 2.69 meter only. It is because in laminar or turbulent theoretical, we develop their equation by assuming boundary layer start at x equal to 0 and delta equal to 0. So, and then if we check the value of 2.69 meter in Reynolds number, we found that it is 8.4 times 10 to the power of 5. So means that it is turbulent. So, and then we could calculate the value of delta by using the 1/7 power law equation. So here we could get the value of delta is 0.0668 meter. So this value is more accurate compared to the first calculation because if we assume it is 100% laminar boundary layer, if we neglect the laminar boundary layer, so mean we assume it is 100% turbulent boundary layer, so the delta is 0.0917 meter, which is 77% higher compared to the our second calculation here. And then we need to calculate the drag force. To calculate the drag force, we cannot use drag force equation for turbulent boundary layer alone because the distance or the length is shorter than the original length. And then for sure, laminar boundary layer give certain resistance. I mean the existence of laminar boundary layer will contribute a drag force to the system, to the problems here. Okay, the idea is very simple. We have a plate here, and then if we assume we have a turbulent boundary layer at this one, so we cannot just use this length to calculate the drag force because we have an extra drag force contributed by the laminar boundary layer here. So what we do is, so in this case, we use CD as shown below in this calculation. So we found that the CD, according for the X, is equal to 4 meter. So we have is 1.25 times 10 to the power of 6. So and then we use the CD of this one. So if you see the equation, so this CD is actually the CD that we could get from the 1/7 power law, but we need to minus with certain amount of value here. So this value is actually, if we assume it is 100% turbulent here, so we need to deduct with the amount of this one. Okay, this value, okay, this area that is actually represented by this number. And there are no specific method, or we cannot just calculate from mathematics to get this value of 1700 over Reynolds number. It is actually comes from the curve fitting or the experimental works. Okay, later on I will explain. Just for this solution, so we calculate the CD by using this equation, and then we get it is 0.00304, and then we could calculate the drag force. It is equal to 0.885 Newton. So this is actually the guideline of the CD that we could use. It depends on our critical Reynolds number. If the critical Reynolds number is 3 times 10 to the power of 5, so we could get this one. So if we have a critical of 5 times 10 to the power of 5, so we get this one. So if our critical is 6 times 10 to the power of 5, so we use this one. So this value is actually from the curve fitting, from the evaluation of experimental and our numerical method. So and then how to determine the critical number here. So the critical mean the changes, the transition between laminar and turbulent. So you could use the idea in chapter 5 by using the idea of Harkness-Kahn and Twitch to determine the critical condition of your boundary layer problems. Okay, so and then another next in tutorial, maybe next week I will a few question at the last of this subject. I will show you how to get the about this by using the equation later on. So at this moment, so it is good to have this idea, the calculation of laminar and turbulent boundary layer by looking this table.